Well, thank you very much for the introduction. Thank you very much for the invitation. It's a pleasure to be here. Yeah, I think the previous talks sort of introduced some of the topics that you'll see again in this talk as well. So this is the contact process on dynamic random graphs. I'll explain what that is in a second. So let's just wonder, this is joint work with Natalia Marco Seiler, and Anja Sturm. Okay, cool. So what is the contact process? The contact process is a process that sort of models the spread of a disease. If you want to think about it, it could be information, whatever you want, on some sort of structure population. And what's the important thing about this, there's obviously lots of disease modeling that doesn't think about the underlying structure, but just thinks that everyone has a chance of contacting anyone else. So the contact process is a way of sort of doing this on some prescribed neighborhood structure given by a graph. And well, maybe together with the voter models, the contact process is one of the examples of an interesting interacting particle system, which is relatively easy to describe, but has sort of an interesting phenomenology behind it. Good. And so what are the main questions? Obviously, because you've introduced the structure behind this, you want to understand how the structure influences how the disease is spread across your graph. And what we want to do is what I want to focus on in this talk is what happens if this structure, this neighborhood structure changes over time. So you can sort of see the parallels to the talks that you heard earlier. And in particular, I want to be looking at the case where you have some graph and then there's a switch edges on and off over time. And I want to understand, when does my process still show phase transition? What changes if I introduce these extra dynamics? Good. All right, so I'll reintroduce you to the, hopefully a lot of you have seen this before, the contact process. So to each vertex, we have some graphs, some fixed graph for now, and to each vertex, you associate one of two states, either it's susceptible or it's infected. And then if you are infected, then you infect every neighbor at some constant rate, lambda. So this would be the sort of transition that you see here on the right. This vertex is infected and it infects one of its neighbors, in this case, the one on top with rate lambda. And the other possibility is that a vertex recovers, once it recovers, and then it becomes susceptible again. Obviously, other variations you could be looking at, you could be looking at an SIR process or whatever, but this is the one where you just have susceptible and infected, and then after you recover, you become susceptible again, you can get the disease again if you want. Good. Yes, just some notation. I'll probably call XT will be the set of infected vertices. That sort of fully describes your process. And obviously, as you increase lambda, you infect more neighbors, and so you'll see overall more infections in your process, and so the process is monotone in this parameter, in this lambda. And yeah, and that's sort of, and this is the one question that's sort of a recurring question here is, for a whole range of graphs, you see a phase transition in this lambda. There will be examples when you don't. So just to go back, some of the, so how do we describe this phase transition? There's sort of at least two ways that you could be doing this. So you start with one vertex, you pick one vertex, and that's the initially infected vertex, and then you sort of look at how the disease spreads. And there's this notion of weak survival, and that just asks, well, what's the probability, when is the probability that the infection survives somewhere, when is that positive? Oh, and this is I'm trying to remember this typo. This should not be, it should be unequal to. So when is there some infection somewhere in the system, when is this probability positive? And that's weak survival. And on the other hand, you have strong survival, and this is the notion that if you look at your starting vertex, can I find an infinite time sequence when the starting vertex becomes infected? Cool. So one of them, sometimes the first one is also called global survival. So your process survives somewhere on your graph, but not necessarily where you started. And the other one is more local survival. When does the infection come back to your initially infected vertex? And a priori, these are two different notions of survival. And so natural question is, when are these the same? And okay, if I define these critical values, lambda 1 is going to be the one for when the process survives weakly, and lambda 2 is the parameter when the process survives strongly. Obviously, lambda 1 is smaller than lambda 2 in general. And for very regular graphs, so this is classic for, it was classically defined on the d-dimensional lattice, these two critical parameters are the same. But starting with this paper by Pimentel in 92, and then sort of extensions by Liggett and Stacey, they showed that if you take a regular tree, a d-regular tree, then this lambda1 is strictly less than lambda2. So you have, there are two different notions of survival. So you can have a process which survives globally on your graph, but if you just look at the root, you wouldn't notice that. You sort of would you would die out there. The sort of infection sort of spreads into the infinity of your graph, but doesn't come back. So these, yeah, we'll come back to this in the other case to some extent as well. All right. Yeah, do feel free to stop me if I'm saying something. I'm doing too quick. Yeah, question. Just the one, you pick one vertex and that's infected. Yeah, okay, cool. All right, so what kind of graphs are we interested in? So well, you can probably guess we're interested in trees, and because this is a meeting on random graphs, we are interested in particular random trees as your underlying graph. And so we'll focus on Bienname Galton-Watson trees. So that's just a graph where you start with a root that has a random number of children, and then each of these children again has a random number of children with the same distribution as your starting vertex. And these graphs often arise, as you've just seen a couple of minutes ago, as the local limit of sparse random graphs. So I've sort of, my simulations are not as good as the ones this morning. I just sampled an Erdős-Rényi random graph, and then if you sort of look locally, you'd pick a vertex, not uniformly chosen, but in general uniformly chosen, and you look at its neighbors and you look at the neighbor of the neighbors, then what you see is pretty much a tree, almost. And this is obviously a very small graph, but if you did this in a big Erdős-Rényi graph, you could go a fair bit. And what you see is a Galton-Watson tree, and if you do this for other random graphs, model like configuration, model inhomogeneous random graphs, you still see a Bienname Galton-Watson tree. You have to be a little bit careful because the root has a slightly different distribution than the children because of size biasing. But you see a Galton-Watson tree, and to a certain extent, everything I can say about the Galton-Watson trees can be translated to the random graph setting. And just for simplicity, and because that's what we proved most of the results, I'll be talking about Bienname Galton-Watson trees rather than the random graphs, but there is this option of translating. In fact, for the second half of my talk, I'll come back to the random graph setting. So I'll start with the branching process ideas first. Okay, good. And so what is known in this case, if I don't have any updating, if I just have a static graph, I sample this graph once, and then I let my contact process run. There's sort of results, sort of series of famous results, maybe about 5 to 10 years ago now. That sort of sparked a lot of interest in this area, and that these results by Mediatel and Wang Direct, and there's some sort of earlier works that sort of indicators where these things would be going, but this is sort of quite essential for how this field developed in the last few years. So what does it say? Well, you take a Bienname Galton-Watson process, so zeta is going to be the offspring number, the number of children I have at each step, and for simplicity, I would assume that I always have at least one child, so my process can't die out, and the mean then obviously is bigger than 1. I don't want to trigger a case. Okay, and then there are two cases. So if the zeta is reasonably well behaved, so it has some exponential moments, then the process behaves similarly. Then the process behaves similarly to the lattice. So you have a phase transition. So if you have there's a positive lambda, so that if your lambda is less than this, then your process survives. However, if your offspring distribution is more heavy-tailed, so if it's sub-exponential, so you've got no exponential moments, so this expectation here of e to the d times zeta is always infinite, then your process doesn't show a phase transition, and however small you choose your lambda, your process will survive strongly. Okay. And so what does this tell you? Well, this offspring distribution sort of encodes how inhomogeneous the degrees are that you can see in your graph. And if you don't have these exponential moments, then you're quite likely to see relatively large degrees in your underlying graph. And this then says that there are some what I'll be calling stars from now on, so vertices with large degree, where this infection is just maintained for a really long time, and that sort of drives the survival of the process. And so that even if you choose your lambda really small, your process will still be sort of maintained by these stars. Okay. And as I said before, all these results can be translated to random graphs that converge locally to these Watson trees. You have to then sort of say what survival means in this case, because it's a final graph, it'll die out. So the transition, well, you have to be a little bit careful. It's not completely trivial, even if I'm maybe pretending here that it is. So survival some means, in the easiest case, that you have exponentially long survival of your process on your random graph. And then you can translate this result as well. Good. Okay, so this is a static case.
You must always start from an infinite graph, because otherwise you will never you'll die out immediately. So the class of graphs that you have to consider is anyway infinite. So is it some sort of tree-like infinite object that will converge locally to your BGW?
Oh no, sorry. Yeah, if you can start with finite graphs. And then you can just ask, how long does this process survive? It will die out eventually, but in the case when it survives, it'll just survive for an exponentially long time in the size of the graph. Yeah, thanks.
I have another question. So
yeah,
these are all amenable graphs, right? What you'll get in this collection.
Yeah. So
does the geometry come into play in these conditions or no?
It's a really interesting question. I've got one example. Well, I think you could do sort of long-range models where some stuff is known. So you can do some stuff in spatial models. But it's a good question of whether this is sort of driven by, well, I don't know, this sort of tree-like, this exponential growth, as you say, or not. We have some ideas. But it's an interesting question. What drives this? And it's not fully understood. That's actually a good point. All right. Okay. So now I'll sort of describe our model. So we're interested in this case when the underlying graph changes over time. But we sort of have a base graph. So we fix we've got Watson tree, some offspring distribution, and this graph sort of encodes the potential neighbors. So that's all the people you know, all the people that you can possibly interact with, but you don't interact with all of your friends at the same time. It's maybe quite realistic. And so you only interact with those edges which I'll be called opening. So I'll start by independently just percolating my tree by just declaring each edge open with some probability and otherwise closing this edge. Now, in this probability, I'm choosing to make my life harder if my degree is already large. And I do it in a very specific way, and we can come back to this. So the probability that an edge xy in your tree is open is proportional to the product of the degrees to some power minus alpha. So this alpha here sort of encodes how much you penalize vertices that have high degree. So the idea is sort of that even if you have lots of friends, maybe you're not always in contact with all of them at the same time. Maybe even if you're really popular, there's some constraint on you. Yeah. Yes, yeah. Sorry, yeah. Right, exactly, that's important, yeah. So.
Okay, so I just asked whether X and Y must be neighbors in the tree.
Yeah, they are. I didn't write this down, but yeah, they are.
Okay, thank you.
So the base graph's always fixed, and then I percolate this base graph. Okay, so the idea is that, yeah, if you have a large degree, maybe you're great, you have lots of friends, but you can't stay in contact with them at all times. And so alpha is this parameter, maybe I should remember this, is this sort of penalization, which tells you how many friends you're in contact with. Okay, all right, maybe I don't understand. And then you have another rate I need to tell you is how frequently you change who you're in contact with. And that's given by some rate, which in this case will just be, again, use some flexibility is the maximum of the degree of X and Y to some power eta. So the larger eta is, the more I'll be updating, right? So I guess if you have lots of friends, then you're very busy, and so you change very often who you're in contact with. Okay. Yeah, there are some other choices you can make here. You could And I can say some stuff about some of these, but our results look best for this sort of product case up here and here. Okay, there's more flexibility. Okay, I should tell you, when I update, then I just repeat this whole process. Then I open this edge with probability P, and otherwise it is closed. Okay. So yeah, again, so the thing to remember is that the larger iter, the faster the updating happens. Good, and then obviously what I'll do to my contact processes, I'll let these two dynamics evolve at the same time, and the restriction is just the contact process can only infect via open edges, right? So if the edge is close to a friend, that I can't infect that neighbor. Yeah. Well, I want them to, so the question was why there's a reason for this particular choices. It's a good question. Well, I want some effect. Can you repeat the question? Yeah. So yeah, I think yeah. The question was just why these particular choices. I want some sort of function that depends on the degree. So if you have a large degree, I know that it's going to play an important role, so I want to penalize these more in this case. And then you have some choice. You can take the maximum there, and we get some results, but product is nicer for us and at the moment. Good. All right. Okay. Just to quickly, I'm not sure I need to do this picture. So you have your underlying graph. You initially declare some edges open, and then you update. Maybe this edge updates, and then I decide, do I keep it open or do I close it? This case, I close this edge, and so so the root, for example, is now disconnected from all this part, so it can't infect anyone else, and so on. And the reason why I did this picture is I wanted to show you that it's not quite clear what the updating does to the dynamics. On the one hand, it obviously helps because it now opens up edges and sort of give me access to part of the tree that I couldn't get to before. On the other hand, it obviously also makes my life harder as an infection because it also disconnects me from other things. So it's not clear what the updating does overall to your system. Is updating helping you or not? And in particular, the question we want to answer is what happens to phase transitions if my original model, say on the percolated tree to make it fair, has a phase transition or does not have a phase transition. Let's say it doesn't have a phase transition. Can the updating induce a phase transition? Good. All right, so these are the questions. All right, I have a slide on previous results. So these sort of dynamic, the dynamic models are interesting. Mostly they've been looked at in some regular trees. So this original paper by Broman, who sort of introduced this for bounded degree graphs. Then there was a paper by Link and Remnick, who looked at this model on ZD. In particular, they have this interesting phenomenon where you can see that updating helps you. And they have a sort of a new transition in the P1 there. So if P is very small, you get this immunization phase. So even if your update speed is, if your update speed is very small, you can choose it small enough so that the process does never survive. So the lambda critical in that case is sort of infinity in some sense. And or if you're above this P, then you always survive if you choose your lambda large enough. So there's some sort of new phase transitions in these models that can appear. And interestingly enough, there's some original work in one dimension and then in larger dimension. That was a recent preprint where it shows that you can take a graph that's initially subcritical. So the P is less than the percolation critical value. And then you can still have your process surviving, your contact process surviving on there because of the updating. So there's loads of interesting stuff. There's some results by some of my co-authors on more general graphs, particularly long-range percolation models, I guess, a bit in your question, which are not tree-like, where you can show some more results about these graphs. And there's one other paper that does these on random graphs. They have a series of paper with updating random graphs, but there's one where they do edge updating, and it looks very similar at first sight. And they take an inhomogeneous random graphs, and then at a certain time you'll look at your edge. When it wants to update, it just forgets that it wasn't that it had this connection and just choose a completely at random in the sort of out of all possible vertices, and that has to a certain extent very similar dynamics to us. but it's not constrained to this underlying Golden-Watson tree. So it's a bit like a question I had earlier. Locally, these things look very similar, but I can't see a way of sort of translating them from one to the other. Maybe you can tell me how to do it. So good. So here is our first main result. So we take our sort of updating the probability that I'm connected, that an edge is open, is this p given by the product of the degrees and power. Then I've got an update speed, which is the max of the degrees, some power eta. So alpha and eta are these two important parameters. And I'll first show you the result when the underlying offspring distribution has a power law. And in that case, I've got this sort of very neat phase diagram. And I've got one region, the yellow region up here. So you probably don't need to read this, just look at this picture. There's one region here where I do get a phase transition. So that's as for a bounded degree graph. Whereas down here, I've got I don't have a phase transition. So that's what you expect for the standard binomial Golden-Watson tree. And so if you look at this in terms of the eta, if eta is equal to 0, then I've got constant uprate speed, or you can think of as sort of no updating, and then you can compare it to the just percolated graph now. And in that case, well, if the alpha is bigger than 1, in fact, then this so the expected degree is less than 1, and so you're almost like a bounded degree. But what you can see here is you increase the eta. There's sort of a region where you don't behave like where this penalization sort of kicks in, and you don't behave like the static case. I'll explain that in more details in the next few slides. Okay, so for now, this is just the phase transition. Yeah, here we go.
And the beta doesn't play a role?
No.
Okay, that's
well, there is Subhra. Yeah, but it's sort of, well, is it? Well, because you don't really get a transition if you're just looking at like a Golden-Watson tree or something with just in the static case you always survive, right? So yeah, maybe it is a little surprising.
Maybe just
I can make it reappear though in a minute if I do something in a minute. Another question?
One question like same with Nelly's, like if you have infinite mean like of the progeny distribution, you have shouldn't something like Duret happen, like you have a star and this thing should vanish, like lambda 1?
Yeah, so this is the regime down here where you don't have a...
Yeah, so in the, so I'm a bit...
Oh wait, hang on, did I miss an assumption? Maybe...
Because, so in the first part also the beta is general, like if you take infinite mean there...
Oh yeah, okay, do I? No, I don't think so.
Beta infinity.
No,
I mean, so beta between 1 and 2 has infinite mean, right?
Yeah, sure. I think that's fine. That's fine.
Dynamics that makes it different.
Yeah, exactly. In this case, there's the dynamics that sort of push you away from no phase transition. Exactly. And so, yeah, exactly. I'll explain this a little bit better in a minute. So just to compare, maybe I'll sort of go through this result a little bit more slowly. So in the slow speed regime, so when eta is small, you can compare to the static case, but you have to sort of compare to the percolated tree. So I just have to convince you, you still have a power law tail in that case. You can calculate it. It's no longer the original power law tail. It changes, and it's now, well, I guess it's beta minus alpha divided by 1 minus alpha. So it changes, but it's still a power law. So if you were just running your model on a static tree, you would expect lambda 1 and lambda 2 is equal to 0. And so and what we see is that the dynamics sort of change this picture. Oh yeah, and I should say this is for alpha is less than 1, right? Otherwise this doesn't make sense. So if you look at this picture here, in this bit here, on the static tree, you would see lambda 2 is equal to 0, which is what we see if the dynamics are very weak. So that corresponds to our picture for eta is equal to 0. Have I changed between etas and, no, that's okay, right? Okay, so there's one small difference here. If you take just a constant speed, v, then you can still have that the percolated tree at time 0 is almost surely finite, but because you're allowed to update edges, you can still survive. So the updating helps you in this sense, helps the infection in this case by opening up space. So that's 1 point. In the fast speed regime, well, if you updating really quickly, then before every infection attempt, if you sort of discretize time, you immediately see sort of an update. So effectively, infection rate becomes lambda times this p. And this is exactly what was introduced as the penalized contact prices by Bartkomjati and Balazine, and the paper got published in 2026. It's, yeah, the preprint sort of appeared a little bit before ours. But we knew of their work anyway. And so their result says that by penalizing your degrees, by saying that the infection rate is smaller if your degree is large, you also can sort of mess around when this phase transition happens or not. And particularly if alpha is less than a half, then you don't have a phase transition, whereas if alpha is bigger than a half, you do. And so if you compare that to our picture, this alpha is equal to a half is exactly what happens if eta is big. Then you sort of see this transition appearing. So this effect here on the very right is what you see is the fact that the infection rate is effectively penalized. So vertices with large degree also have smaller infection rate. Okay, so this is the fast speed regime, which corresponds to this penalized contact prices. And in fact, you can, just going back to some of the original work by Broman, he has this coupling lemma, which allows you to sort of couple this infection rate, which is modulated by this on-off edge, to just a normal exponential. There's a relatively, it's a nice lemma in there, which tells you that you can couple these random variables, and so you can couple a penalized model to our model. And in particular, that shows us if the lambda is 0 for the penalized model, it's also true in our case. So this blue region down here, we sort of get for free from their results. It's a lot of work for them. But, okay. Good. So yeah, just to recap, for slow speed, behaves like the static model in some sense, at least to when you want to understand when there's a phase transition or not. And for fast speed, it behaves like the penalized model. But there's also an interesting intermediate regime where you sort of interpolate between the static model and the penalized model if you choose your update speed corresponding.
What happens with this zeta of p when alpha is larger than 1? Then you still have a power law, right? But the formula doesn't seem to make much sense.
No, exactly. Do you still have a power? What happens? I don't know. I didn't calculate. It's a good question. So what happens in terms of the expected number of neighbors do you have? It's like zeta times zeta to the minus alpha, right?
You basically then kill all of them for high degrees.
Exactly. So then something changes there.
Thank you very much.
Good. Yeah, that's a good point. Oh, sure. Clearly disappeared from my slide. Okay, cool. What am I doing for time? I think I'm going to skip this. So you can also do some stuff for stretch exponentials, and then the picture isn't quite as nice, but I'm going to skip it because. But then you can sort of see, as you saw for the static case, what happens. The transition is when you have exponential moments or not. So stretch exponentials is sort of somewhere where you can test things, and then you can see that our results, the phase diagram we expect depends on the experiment in the stretch exponential. Unfortunately, there's still a bit of a gray region here, which we can't fill yet. But expect this blue thing to be right, and everything up here should be yellow. But okay, I'm just going to skip this because I want to get to some other stuff at the end. All right. Right, so how do we show this? And there's sort of now, well, I guess sort of a standard argument for at least that, for the case when you want to show that there's no phase transition when lambda 2 is equal to 0. So I want to show that, the root is infinitely often infected. Sorry, again, I forgot to change something. All right, so this is sort of going back to an argument by Piedmantel and then Wang adaptive, and I guess, and there's sort of variations of this. So the idea is that you have big vertices with big degree that maintain your infection for a long time. And what you want to show is that your root is a star, and then it survives there for a long time. And in that time, you can pass the infection to the next star, and so on. And then sort of, that way you can bring the infection arbitrarily far into your tree, but at the same time, you can also bring it back to the root infinitely often. And so what you need to understand is what the dynamics do on the star graph, sorry. And here you can also see how the sort of dynamics, the local dynamics of opening and closing edges feeds into. Yeah, good. Okay, so you take a star graph. This is my center, which is infected. So how do I maintain the infection for a long time? Well, I'm going to infect a certain proportion of my neighbors very quickly. And then even if this the center dies out, because I've got lots of infected neighbors, they can sort of reinfect me quickly, and that way I can survive for very, very long times. By just going backwards between the center and the neighbors. And so at time 0, I've got about n times p vertices that I'm connected to via open edges. And so that's n to the 1 minus alpha in my notation. And then the update speed is n to the eta. So how do I infect this? Well, I can infect it to one of these open neighbors, and I have to do it before this edge updates. And so the probability that I do that is roughly lambda divided by all these sort of other things that could happen. So there could be another infection, there could be a recovery of the center, and there could be an update. That's these rates here. But these don't really matter. What matters is the update speed, if that's large. So then I'm successful infecting order lambda times n to the 1 minus alpha minus eta number of neighbors before that particular, before the corresponding edge is closed. Okay, that's the sort of number of edges I can get infected immediately. And then the probability that all of these fail in reinfecting me in the sort of next, before they recover, is given by the probability that they update or recover, divided by the corresponding rates. And if I work this out, this gives me an exponential term, which is e to the minus lambda squared, and then the exponent is 1 minus alpha minus 2. Okay? And so this is the probability that I fail of maintaining the infection in one of these interactions. And then you can sort of see that as long as 1 over this is much bigger than 1, then you can sort of survive in for an exponentially long time, because you just can keep trying doing these. Okay. And yeah, okay. And this sort of tells you if alpha plus 2 eta, if alpha is less than 1 minus 2 eta, then I'm in this regime where this works. And I can then survive for an exponentially long time. I should probably say this sort of strategy works if eta is in this intermediate regime. If the update speed is large, this is not quite the right strategy. I have to be a bit more careful, and I also have to try and infect some neighbors that are currently closed. But because the edge sort of updates very quickly, I have a chance of doing that in a reasonable amount of time. And the advantage is that I obviously have loads more neighbors that I'm connected to by closed edges. And so even though they're not open at the moment, I can sort of wait a little bit and they update quickly. And then they can reinfect me again. So there's something that changes that you can sort of see the difference between the intermediate and the fast update regime. And then, okay, so then now you understand, useful timer here, then this sort of explains how things work out locally. And all these calculations you can sort of make, well, you just need to understand what happens along one edge. And in the end, it's a relatively easy Markov chain, right? You have a state that tells you whether your edge is open or closed, and you have some transitions that only allow to transmit when this edge is open. So you can work out a lot of things. For example, you can work out the probability that you infect from X to Y before X recovers. You can work out these things explicitly. It's a, I don't know, 4-state Markov chain calculation or something like this, and you can do that. And that, yeah, allows you also, okay, you understand what happens at the start, and then you sort of try and push the infection to a certain distance, R. I have to now think about it. Yeah, okay, fine. I'll explain this. This part is now classical, I guess. So the probability to pass your infection to some distance R is now some function of lambda to the power R. And you know you can do it in sort of order R times. And so now you know that this thing here is infected for some exponentially long time. And so if you try S over R number of times to pass the infection from here to there, then the probability that you're successful is, you can work it out, and it's given by 1 minus e to the minus this probability to pass it along one edge to the power r times s to the r. And that gives me a condition on r and s, right? I can sort of relate the distance, how far I can spread it, to how long the infection survives in the star. And at that point, I can sort of need to show how, where do I find the next star? Because it's okay to, I need to also transmit to the next star in order for the infection to maintain. So that's sort of another constraint I have. I can, because this is a nice tree, this is where we use this tree structure a lot, is I can work out how far I need to go up the tree to find the next vertex that has degree n. And this is just, okay, because, okay, here I'm clearly writing mu is the expected number, which I'm temporarily assuming is as finite. Mu to the power r times the probability is then the number of stars at level r. And I want this to be bigger than 1. So r has to be much bigger than the log of the probability, and that's where this comes in. And so I have two conditions here. The first condition tells me that I can find the star, and the other condition tells me that I can actually transmit this far, depending on how long my center is alive. And I can sort of solve these equations, and I can check that that gives me a constraint on the probability compared to the size of my stars in terms of all my parameters, which translates into this conditional. Okay, so yeah, hopefully, even if the details weren't clear, this sort of overall strategy was all right. So I'm going to skip this. The sort of upper bound is much more deterministic. It uses martingale argument. It doesn't really rely so much on the overall structure, which is good, but also bad because it's not quite good enough in all the cases that we wanted to cover. What I want to talk about the last few minutes is just sort of a quick sort of advertising for our future work. And it comes back to this question on studying the model on finite graphs, say on a configuration model with n vertices. And a typical question that, well, as we discussed before, is, so you know, if you can start your whole process with everyone infected. After some time, the process will die out. And in this sort of supercritical regime, and this is something you get if you have power law tails, then the process survives for an exponentially long time. But what happens is that you see these metastable densities. So everyone's infected initially, then the total number of infected vertices sort of dies down to a certain proportion. And it's interesting, which is, yeah, this proportion then maintained for a long time, and then it dies out. And it's interesting to calculate this, and so we can do this as well. So this is my process with everyone infected, and I want to know what is the total number of vertices that are infected at some large time Tn, not too large, but sort of intermediate times. And I can calculate this using duality. So this proportion here is obviously very close to the probability that a uniformly chosen vertex in my graph is infected at this time. And then by duality, which just means you sort of reverse all the time errors. And the contact process is nice in this way because you again get a contact process, and all you have to do is sort of switch the initial conditions. And so if you reverse time, you start with one initial infected vertex uniformly chosen, and then you just ask, is there someone that's still alive at this time Tn? And this probability here is just the survival probability in the limit of a Golden-Watson process, right? So if I want to calculate these metastable densities, what I really want to know is what are the survival probabilities for the contact process on a Vienna-May Golden-Watson tree. And I guess, yeah, I only have 1 minute, so I'm just going to show you the results, and I've sort of and you can calculate the survival probability in this case as well, and you see that there are two different regimes. And now the power law really comes in. In the survival probability, you see the power law appearing. That's the beta here. For small beta, there's one regime where, well, I can tell you what the function is, but I didn't write it down here. And then you sort of have a linear increase in this probability. So rather than telling you what the formula is, I wanted to just tell you that there are two different strategies which determine the survival probability. In this case, the first one is a strategy where you sort of just try and spread your infection directly outwards at all times. So you always just ask, can I infect my child effectively before I recover? And this works for very small beta because you have, as we said before, the underlying P-NME Gaussian trees has infinite mean. So you have a lot of children, so you have a lot of trials, and you can then approximate your process by a process on a truncated tree, and then calculate the survival probability on this truncated tree. I have 1 minute, or? And then the second strategy is that you assume that the probability is essentially dominated by your starting vertex being a star in exactly the same sense that we had before. And then the survival probability is exactly just the probability that the root is a star. And then all the work goes into showing that if your initial vertex is a star, then you can sort of transmit the disease. Yeah, and then you get that again lets you calculate these experiments. I'm happy to explain more to you over the next week. But I think I'll finish here. There's still a few open questions in this area, and definitely sort of direction of when you have your dynamics interacting with your infection is very interesting, but also very hard as we find out. So yeah, I'll stop here. Thank you very much.
Thank you, Marcel. Questions?
What makes this prove that lambda 1 is strictly smaller than lambda 2 so hard for trees?
It's a good question. I haven't actually tried, but I'm pretty sure that at least the Bamidi et al., that's what they were trying to aim for. It's a good question. Yeah, I don't know. Does anyone? Yeah, but I guess you'd. No, I don't know. I can't give you a good answer for that.
Yeah, actually, I was wondering if you could basically translate some of this language to get a kind of like voter model dynamics where like people can change their opinions by themselves, right? So let's say some reflecting or critical thinking or whatever.
Oh, okay.
Effectively, right? Because it's like you start with somebody's infected, they could transmit the infection to others, aka transmit their opinion to others. But it's also possible that they could recover, meaning that they could like they could change their opinion by themselves to like some kind of thinking once they're at that different opinion. So I was wondering if you could just translate the language, could we get some kind of regime in that setup with these techniques over here?
Yeah, that's an interesting idea. We should talk later.
Now, one of the problems with the contact process is that it doesn't have a nice dual. It has itself as a dual.
Yeah.
So that makes many of the things that you want to do hard. So is it true that many of the things you do is through some form of comparison with percolation?
Yeah.
So is that the kind of red thread that you always have to deal with in the various different settings that you were talking about?
I think a lot of things you can do that way. Obviously, I don't know. Some sort of comparison with branching processes, but maybe that's just percolation.
Yeah, okay.
But yeah, exactly. Yeah. Sure.
Okay, thank you, Marcel.
Thanks.